Hello, everyone, and welcome back to another week of our Math Virtual Learning Session. So this is week number 6 and day 10. Um, Last week was our week 5, and we didn't do we didn't do a math session on Friday. So we are entering into a new week. This is week 6, and this is day 10. Now, as you guys can see, Andrew, he is not here to do his part of the math session, but he'll be back on later on this. Ooh, I'm so sorry. I apologize. My allergies have been acting up, so probably throughout this math session, you guys, you probably hear me sneezing. So I would try to mute myself when that happens. But anyways, he is not here to do a math session with us on today. Hold on just a second. Okay, as I was saying, he is not here to do another math session with us today, but he will be back on later on into the week, either Wednesday or Friday. Now, as you can see, I said Wednesday because this week we will be doing 3 math sessions to make up from on last Friday since we didn't do one. So math session today, on Wednesday, and on Friday. So here's the schedule for this week. Well, for me, and then Andrew, he will tell you guys his schedule either Wednesday or Friday when he returns. But for me today, we are still, you guys, dealing with fractional and irrational numbers this week. So today we will still be doing rational and irrational numbers. I'm gonna give you guys some examples and show you guys some videos and refer back to the notes that we did on last Monday. Then on Wednesday, we will be reviewing. That would be a review day of rational and irrational numbers on that. So on Wednesday, it's going to be the last day of rational and irrational numbers because on Friday, we will be introducing I will be introducing a new lesson on scientific notation. So I'm very excited for that lesson. So let me get started here with my lesson on today because I'm just the only one here. So let's get started with my lesson, you guys. So let me show you guys. Well, let's refer back to the notes on last week on Monday to get you guys caught up and just, a recap of it. So let me share my screen with you all. All right, here we go here. All right, here, and I'm going to hide myself for just a second. All right, so last Monday, we talk about rational and irrational numbers. I can identify rational and irrational numbers. So as you can see here, a rational number is any, and circle or underline any because I got that in italics. And I can't circle or highlight it at this point now. But highlight that, underline, so you know, because it is any number, you guys, any number that can be written as the ratio of 2 numbers. And as you can see here, I have an example, A over B, which is in a fraction form, where A and B are integers. A and B, they are integers, and B, it does not equal 0. You see, I have that bold and underlined and highlighted because it does not equal 0. So a rational number, it's any number, you guys. It can be any number that is a whole number, of course. That is a whole number, and it can be written as a fraction. And I have some examples down here, which I'm going to show you guys. Again, then we're moving on to an irrational number. It's a number that is not. It is not rational at all, okay? Irrational numbers are not rational. It cannot be written as a fraction. It cannot. And as you can see here, irrational numbers cannot be represented by a terminating or repeated decimal. Do you guys remember when we talked about this during the first week of our math session? A terminating or repeating decimal. If not, refer back to those notes. and search it up on our YouTube channel. It's the first week. I'll discuss this on day one. So search up on our YouTube channel. It will have title Math Virtual Learning Session Week 1, Day 1, and here's where I discuss terminating or repeating decimal. I'm not going to talk about it here because you guys should know it. So it cannot be represented by a terminating or repeat decimal. It cannot be. So here are some examples that I have down here. And make sure if you haven't copied down these examples already, please do take a picture of it, screenshot it. Do that quickly. Now, as you can see here, and I wish there was a way that I can zoom in. Here we go. Yeah, here we go. Let's see. Hopefully this will work. I don't know. No, that didn't do nothing. But anyways, as you guys can, I'm so sorry, you guys. My computer has been. You can see. Look at there. My computer has been acting up for days now. So okay, I should have left this alone, and you guys can't really see it. So hold on. Give me a second. Okay. Here we go. Now, as you guys can see, as the example I have down here, a rational number, it can be written as a fraction. I have it down. And then when I have it over here, irrational number, it cannot be written as a fraction. And then here are some examples of a rational and irrational number. And then here are some more examples up here. And today's video will cover this right here, explaining all of this here. I have a video of that. So make sure you copy all this down. Copy all of this down. Take a screenshot. Perfect. Stop and share now. All right, so that was a little recap of last Monday's lesson of rational and irrational numbers. So let's hop right into some videos of where I will be, well, actually the videos are, but me as well, I'm going to be talking through it. I'm going to be stopping and pausing, explain this into more detail. So let me share my screen again. I'm not going to say one more time because I will do this again. So our first, and let me share my computer screen. My computer sound to where you guys can hear. All right, so the first video that I have is we are going to be recognizing rational and irrational numbers. So, and this is from Kyan Academy, excuse me. I just love their videos here. So this video, you guys, it's going to give you a bunch of numbers here as it has here, and it's going to tell you guys which numbers are rational and irrational numbers. So pay close attention to this video. It's just 2 minutes long. So make sure you take notes, get out your pencil and your notebook and take notes. All right, here we go with the first video. Pay close attention.
Which of the following real numbers are irrational? Well,
I'm so sorry, guys.
Irrational just means it's not rational. And it means that you cannot express it as the ratio of two integers. So let's see what we have here. So we have the square root of 8 over 2. So square root of 8, if you take the square root of a number that is not a perfect square, it is going to be irrational. And then if you just take that irrational number and you multiply it and you divide it by any other numbers, you're still going to get an irrational number. So square root of 8 is irrational. You divide that by 2, it is still irrational. So this is not rational, or another way of saying it, it is irrational. Now you have pi, 3.14159. It just keeps going on and on and on forever without ever repeating. So this is irrational, probably the most famous of all of the irrational numbers. 5.0. Well, I can represent 5.0 as 5 over 1. So 5.0 is rational. It is not irrational.
Because it's a whole number. It's a whole number. What he just told you guys, that you can write this as 5 over 1, which gets you 5. And that is a whole number, which means it is a rational number, not irrational. Okay? And then what he has circled is irrational number, because that's in the question. Which of the following real numbers are irrational? You have the square root, the first, the square root of 8 over 2. That's irrational, because what is the square root of 8? What's the square root of 8? And then over 2. That will be irrational. And then you have pi, which that is 3.14, whatever the rest of the pi number it is. So that's irrational.
0.325. Well, this is the same thing as 325 over 1,000. So I can clearly represent it as a ratio of integers. So this is rational, just as I could represent 5.0 as 5 over 1. Both of these are rational. They are not irrational.
Correct.
Here I have 7.777777, and it just keeps going on and on and on forever. And the way we denote that, you could just say these dots that say that the 7s keep going, or you could say 7.7, and this line shows that the 7 part, the second 7, just keeps repeating on forever.
Correct, you guys. I forgot to mention there are 2 ways that you can write a repeating decimal instead of writing it as it has up here. For example, 7.7777777 keeps going on and on. There's no reason for you to write all those numbers, because it's going to keep going on, you guys. It's going to keep going on. So there's no reason for you to write all that out. So instead, there are 2 ways you could do it. You could write it as it has up here, 7.77 ... which that means that's a repeating decimal. Or you could do 7.7 and put a line over the second number, which represents a repeating decimal. So there are 2 ways that you can write a repeating decimal instead of writing it out, because it's going to keep going, you guys, forever. The number is going to keep going on forever. So write as 7.77 ... or 7.7 and put a line over the second number. Okay.
Now, if you have a repeating decimal, in other videos we'll actually convert them into fractions, but a repeating decimal can be represented as a ratio of 2 integers, just as 1/3 is equal to 0.333, on and on and on, or I could say like this, I could say 3 repeating. We can also do the same thing for that. I won't do it here, but this is rational, so it's not irrational. 8 1/2.
You understood that? Did you understood that? He said that's rational. I don't think you guys heard. Let's do this again.
As a ratio of 2 integers, just as 1/3 is equal to 0.333, on and on and on, or I could say like this, I could say 3 repeating. We can also do the same thing for that. I won't do it here, but this is rational, so it's not irrational. 8.
Now did you hear it? Hope you did. Hope you did.
8 1/2. Well, that's the same thing. 8 1/2 is the same thing as 17 halves, so it's clearly rational. So the only 2 irrational numbers are the first 2 right over here.
So the first 2 numbers are irrational. Then you have the rest of the numbers. They are rational numbers, because they are whole numbers, and they can be written as a fraction. Okay? So that's the end of that video there. So let me go on to the second video, and then I'll probably have to stop the share again and then do it again to where you guys can be able to see the video. So let me stop the share because I don't know if you guys can see that. So let's stop it and then reshare it. So I hope you guys was taking notes. So let's go on to our second video, which is we're going to be identifying some rational numbers. And this is a 5-minute video, so get prepared. And as you can see, this example problem right here, it has look at the numbers below. Identify which numbers are rational and which ones are irrational. So it's basically the same thing as the last video, but it's going to show you guys how are you going to be doing this, and there are lots of notes that you guys will be taking, so get prepared. And here we go with this video here. So pay attention, 8th graders, and also to the 6th graders who are watching this as well. I hope you guys haven't left of this math session here since Andrew is not here. Andrew, he will cover rational or irrational numbers like he told you guys last week that he will be referring to my lesson, but and he may use some of the exact same examples, but switch the numbers around a little bit. So 6th graders, if you are still on here watching this, please pay attention to my lesson as well, because you'll be doing this in 6th grade, in 7th grade, and 8th grade. So pay attention to my lesson as well. Okay. And also to the 8th graders, not only you pay attention to my lesson, but you also pay attention to Andrew's lesson, because you guys know those lessons there. And it's just, like a little recap of it. So 6th graders, you pay attention to my lesson as well. And my 8th graders, you also pay attention to Andrew's lesson as well. Okay. So let's get started. Pay attention and take notes.
Look at the numbers below. Identify which numbers are rational and which are irrational. So just as a bit of review, let's review what it even means to be a rational number. So this means that you can be represented as the ratio of two integers. The ratio of two integers. And if you're irrational, by definition, it just means that you're not rational, that you can't be represented as the ratio of two integers. So not rational. So there's some low-hanging fruit over here, because some of these numbers are actually represented as the ratio of two integers. I'll circle those. 194 is an integer, 23,045 is an integer. Clearly the ratio of two integers, this fraction right over here. So it is rational. 1 is an integer, 8 is an integer.
And then also, while you guys are, circling these answers, to make it a little easier for you guys, because I don't know if he's going to circle just only the numbers that are rational and then use a different color for irrational. He probably is. But to make it easier for you guys, if you have pens or highlighters, mark, which one you have circled or irrational, and then which ones you have the other circle or underline, however you're going to do it. Make notes of that's irrational, or if it's rational, okay, to make it easier for you guys. So what he has circled, that is rational, because like he says, 194, that's a whole number. 23045, that's a whole number, and it is in a fraction form. There are two integers, so they of course are rational numbers.
integer. Clearly the ratio of two integers, so this right over here is rational as well. The other ones are a little bit less clear. Here I have 3.66 and then this dot dot dot, I'm assuming means that it's going to keep repeating, so it's 3.6's and the sixes keep going. More typically or often you'll see this represented as 3.6 with a line over just the 6 to say this keeps repeating forever. So first I'm just going to tell you a rule. A rational number is a ratio of two integers, and any number that can be represented as a repeating or terminating decimal
Write that down.
can be represented as the ratio of two integers and therefore is rational. So if you believe what I just told you, that repeating decimals can be represented as the ratio of integers, then 3.666 and so on and so forth, the sixes keep repeating. This right over here is a rational number.
It's a rational number because, like he says, rational numbers, it can be represented by a repeating or terminating decimal. Irrational numbers, it cannot. It cannot. So make note of that. Irrational numbers cannot be represented by a repeating or terminating decimal. Rational numbers can. So in this case, 3.6 is irrational. It's a rational number. 3.6666 is a rational number. Make notes of that. Copy what he has down here. Rational, ratio of two integers. It can be represented by a repeating or terminating decimal. And also with the irrational numbers, I don't know if he's going to do this, but put right here, it cannot be represented by a repeating or terminating decimal. Make note of that. Make note of that right now. These are not complicated, you guys. This is not complicated. It's not hard. You guys are the ones who are making it hard and complicated yourself, because this is simple. This is a simple and easy lesson. It is. If you just look over your notes and read the problems carefully, then it will automatically be easy for you. So hope you just copy down what I just said. If not, oh well, let's continue on, shall we?
Number. And there's a more systematic way of converting repeating decimals into rational numbers. The way I do it involves a little bit of algebra, but just to show you that this can be, I just want to give you an example. If I divide 2 by 3, what does that equal to? 3 goes into 2, no times, but it goes into 20. It goes into 26 times. 6 times 3 is 18. You then have a remainder of 2. Bring down another 0, which is implicitly there. 3 goes into 20 6 times. I think you see a pattern here. 6 times 3 is 18. Subtract. You'd get a 2. Bring down another 0. So 2/3 is equal to 0.66, and it keeps on going, which is equal to 0.6 repeating. So this thing over here, 3.66666, we could write this as 3 plus 2/3, or 3 plus 0.666666, or 3 and 2/3. And now this is just a mixed number. If you represent this as an improper fraction, you then have the ratio of two integers. So 3 times 3 is 9, plus 2 is 11. 11 over 3 is the same thing as 3.66666666, so on and so forth. So I showed you that it actually can be represented as the ratio of two integers. The 12 times the square root of 11 cannot be. And the simple way to recognize that is it is the square root of a prime number. And the square root of a prime number will always be irrational. Square root of a prime. And you can try it on in a calculator if you like, taking the square root of a prime number. But you will see that you will get a non-terminating, non-repeating decimal. And so this right over here, I'll do the irrational ones in orange. This right over here is irrational. Negative 81.25. Once again, very easy to represent this as Very easy to represent this as a mixed number if you want. It would be negative 81 and 25 over 100, which is the same thing as 1/4. And then very easy to represent this as an improper fraction. 4 times negative 81, 4 times 81 is 324. So it's negative 324 and then another negative 1. So it's negative 325 over 4. If that confused you that I multiplied and then I had a negative 1, remember, this negative applies to everything here. It's negative 81 plus negative 1/4 is how you should think about it. Or you could just think of it, how would I convert 81 and 1/4? 4 times 81 is 324, plus 1 was 325, and then you have a negative out front. But the main focus of this is, look, clearly you can represent a terminating decimal very easily as a ratio of two integers. And so this right over here it's a different shade of yellow. This right over here is clearly rational. I'm doing the rationals in yellow, and I'm doing the irrationals in orange. Square root of 3, we have the square root of a prime number. It's going to be irrational. 1.097, terminating decimal. This is 1 in 97 over 1,000, or 97 thousandths. So clearly rational. And then pi, and you'll see other numbers like pi, like e. These are by definition, or by calculation, or however you want to think about it, these are irrational numbers. 3.15, 3.14, 159, and it keeps on going forever. It is non-terminating and it is non-repeating. So it is an irrational number.
So we have 1, 2, 3, 4, 5. We have 5 rational numbers, and then we have 3 irrational numbers. So copy down all of this here. If you haven't already, copy down all of this that he has up here so that it can help you out. I really hope that you are copying this down. Because if not, then I don't know what else I can help you with. I'm trying my best here. Me and Andrew, we are trying our best here of doing these math sessions for you guys. We are helping you guys out. We are helping you guys out. We are like your third teacher here. And if we can't possibly help you out, then I don't know what else. Because your first teacher is obviously is your parents. That should be your first teacher. Then your second teacher is, whoever your teacher is. And then your third will be us. And if out of all those 3 teachers who are teaching you this here, and you still not understanding of how to do it, then I'm sorry. I don't know what else to tell you. I don't know. I just don't know. I'm trying my best. Me and Andrew, we are trying our best. This is just to get us started. Once we enter into that profession of teaching. So we're trying our best here. It's maybe we're probably doing it incorrectly or not doing it as teachers, are supposed to, are doing. If we're doing it totally a different way, well, this is our version of doing it here. And if you don't like it, just head out the door. I don't know what to tell you. But anyways, hope you copy that down. I'm going to stop the share now again, and we're going to go on into our last video that I have. Let me make sure. Yeah. Into our last video, which is classifying numbers with rational and irrational numbers. So let me share my screen for the final time. Classifying numbers with rational numbers. So, and I did it wrong again. Let me stop it because I don't know if you guys can see it. All right, let's do this again. All right, and this is an 8-minute video. So, so in this video here, what I explained early into this lesson, that the notes that we covered last week, that it had this picture here, which I don't know if you guys can see it or not, but it had this here. This is basically this video here. So pay pay close attention. Okay. Really pay close attention. Okay. Sorry, you guys. So let me share this and you guys can watch this here. So 8-minute video and pay close attention. Okay. Pay close attention. Let me do this for the final time. Hold on. Having some trouble. Let's do this again. It's Monday, of course, you guys. It's Monday, so this always happens to us on Mondays. All right, so let's see will this work. Okay.
So we
hopefully, I'm not sure if you guys are seeing this because I can't tell because Andrew's not here to tell me. So hopefully you guys can see it. Hopefully. But if not, I apologize. All right. So hopefully you can see that. All right. Enjoy. And I will be right back.
We have a bunch of numbers listed up here, and my goal in this video is to see if we can classify them into different types of number categories. And let me draw the categories. So this circle over here, this represents all of the numbers that can be represented as the fraction of two integers, and of course the denominator can't be equal to 0 because we don't know what it means to put a 0 in the denominator. So let's call these, or the standard way of calling these things that can be represented as a fraction of two integers, we call these rational numbers. Rational numbers. And if something cannot be represented as a fraction of two integers, we call irrational numbers. Irrational numbers. Irrational numbers. And the size of these circles don't show how large these sets are. There's actually an infinite number of rational and an infinite number of irrational numbers. So these are the irrational numbers. Irrational. So these cannot be represented as a fraction of two integers. And then within rational numbers, you have integers themselves. So I'll do that in, let me do that in this blue color, integers. So integers are numbers that don't have to be represented as a fraction or a decimal. So these are integers right over here, integers. And then a subset of integers are whole numbers. So if you essentially say the non-negative integers, you're then talking about whole numbers. So let me do that subset right over here. So these are going to be the whole numbers. So whole numbers. Whole numbers right over here. And actually, let me just label it all. These are rational. Let me do it in that same color. Rational numbers. And of course, irrational numbers. Irrational numbers. Irrational numbers. And an integer, well, if I could say literally, that is an integer. Let's think about the integers, but I wouldn't say let's just think about the rational. I would say let's think about the rational numbers. All right, now that we have these categories in place, let's categorize them. And like always, pause the video. See if you can figure out what category these numbers fall into. Where would you put them on this diagram? So let's start off with 3. This is positive 3. It can be definitely represented as a fraction. You could represent it as 3 over 1. But it doesn't have to be represented as a fraction. It literally could be just a 3 right over there. But it's also non-negative. So 3 is a whole number. So 3, and maybe I'll do it in the color of the category. So 3 is a whole number. So it's a member of that.
Make sure you're copying this down. Copy this down.
Set. But if you're a whole number, you're also an integer, and you're also a rational number. So 3 is a whole number, it's an integer, and it's a rational number. Now let's think about negative 5. Now negative 5, once again, it can be represented as a fraction, but it doesn't have to be. But it is negative, so it's not going to be a whole number. So negative 5 is going to sit right over here. It's an integer, and if you're an integer, you're definitely going to be a rational number, but it's not a whole number because it is negative. Now we have 0.25. Well, this for sure can be represented as a fraction. This is 25 hundredths right over here. So we can represent that as a fraction of two integers, I should say. It's 25 hundredths. But there's no way to represent this except using a fraction of two integers. So 0.25 is a rational number, but it's not an integer and not a whole number. Now, what about 22 over
you get it. I hope you did.
Over 7? Well, here it's clearly represented already as a fraction of two integers, but I don't think I can represent this any other except as a fraction of two integers. I can't somehow make this without using a fraction or some type of decimal that might repeat. So this right over here, this would also be a rational rational number, but it's not an integer, not a whole number. Now this over here, 0.2713, and then the 13 repeats. This is the same thing, 0.27131313. That's what that line up there represents. Now, you might not realize it yet, but any number that repeats eventually, and this one does repeat eventually, you have the 0.13, or you have the 0.27131313, any number like this can be represented as a fraction. For example, and I'm not going to do it here just for the sake of time, but for example, 0.3 repeating, that's the same thing as 1/3. And later on, we're going to see techniques of how do you convert this to a fraction of two integers. But for our sake, we just know that this can be represented as a fraction of two integers, just the way that 0.3 repeating can be. And so we would put this under rational numbers, 0.2713 repeating, but you have to represent it as either as a decimal or a fraction of integers. If you didn't have to, then it could have been an integer, but we'll throw it up there in irrational numbers. Now the square root of 10. Square root of 10, this is interesting. So any square root of a non-perfect square is going to be irrational. So this is going to be irrational. I'm not proving it to you here, but you cannot represent this as the ratio of two integers or a fraction with two integers, with an integer in the numerator and an integer in the denominator. This will be, if you were to represent it as a decimal, it will not repeat. It'll just keep being new digits. It will not repeat over time. So this right over here is an irrational number. It's not rational. It cannot be represented as the ratio of two integers.
No.
All right, 14/7. This is the ratio of two integers, so this for sure is rational. But if you think about it, 14/7, that's another way of saying 14/7 is the same thing as 2. These two things are equivalent. So 14/7 is the same thing as 2. So this is actually a whole number. It doesn't look like a whole number, but remember, a whole number is a non-negative number that doesn't need to be represented as the ratio of two integers. And this one, even though we did represent it as the ratio of two integers, it doesn't need to be represented as the ratio of two integers. You could represent this as just 2. So that's going to be a whole number. 14/7, which is the same thing as 2, that is a whole number.
Exactly. Or you could also do, how about 7 square? And that equals to 14. You could possibly do that. That may be right, I guess. But yeah. 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 Remember the last lesson? Square roots and cube roots. Remember that? Yeah.
Now 2 pi. Now pi is an irrational number. So if we just take a multiple of pi, if we just take an integer multiple of pi like that, this is also going to be an irrational number. If you looked at its decimal representation, it will never repeat. So that's 2 pi right over there. Now what about, let me do that same, since I've been relatively consistent with the colors. So this is 2 pi right over there. Now what about the negative square root of 25? Well, 25 is a perfect square. Square root of that's just going to be 5. So this thing is going to be equivalent to -5. So this is just another representation of this right over here. So it is an integer. It's not a whole number because it's negative, but it's an integer. Negative square root of 25. These two things are actually the same number, just different ways of representing them. And then you have, let's see, you have the square root of 9 over 7. Well, what's the principal root of 9? This thing is going to be the same thing. This thing is the same. Let me do this in a different color. This is the same thing as square root of 9 is 3. This is the principal root of 9, so it's 3/7. So this is a ratio of two integers. This is a rational number. Square root of 9 over 7 is the same thing as 3/7. Now let me just give you one more just for the road. What about pi over pi? What is that going to be? Well, pi divided by pi is going to be equal to 1. So this is actually a whole number. So I could write pi over pi right over there. That's just a very fancy way of saying 1.
Yeah. Yep. So, I hope you guys, let me stop the share. I hope you guys took notes of that. Sorry guys, I didn't stop, you know, throughout the video this because I just got in my, trying to experience this out. My selfie stick, I just got it from Amazon today, so I'm going to test that out because, well, as you can see now, the light, because I'm currently in the living room, I'm not in my room doing this session here. So the lighting is quite a little bit perfect, but I want it to be absolutely perfect, to where you guys can be able to see me much good and better because I don't like being dark in videos. I don't know why is that the case. Like in pictures and in videos, I'm always dark. So hopefully this will work out. Hopefully this will work out. I'm gonna test this out here. Thank you guys for tuning in with me for another math session with the Future Educators Talk co-hosts. Well, 2 of the co-hosts, not all of us. But like I mentioned earlier, Andrew is not here. He will be back later on this week, either on Wednesday or, well, either Wednesday or Friday. I know he's going to be here on Friday, but I don't know about Wednesday. Probably not. So thank you guys for tuning in with me for this math session here. And our motto is always the same time, same grind, but a different lesson. We do this every Monday and Friday right here on Zoom. So join us live for these math sessions here. And I'll see you guys back later on this week on Wednesday. So until then, take care of yourself and be blessed and have a fantastic rest of your day, your Monday, if you're watching this on Monday, or your Tuesday. So have a fantastic day. See y'all Wednesday.